I welcome you all to my video lecture presentation. Myself C. Ashok Kumar, Professor, Department of EEE, and my course name is Electronic Device and Circuits, and the topic for today's presentation is PN Junction Diode Part 3. And the overview of my presentation goes on like this. First, I will be discussing about the diode equation, and then I will be solving one problem based on this diode equation. And then I will be discussing about the temperature effects on the VI characteristics of a diode. From the VI characteristics, I will be discussing about what do you mean by static or DC resistance, and what do you mean by the dynamic or AC resistance. And also here also once again I will be solving one problem. And finally I will be recapping all the things whatever discussed. Okay, first, and also these are the textbooks I referred. Jacob Millman, the title is Electronic Device and Circuits, and the publishers are McGraw-Hill Education. And second book is Ballstead and Neshelski, and the title of the book is Electronic Device and Circuit Theory, and publishers are Pearson. And third book is the Salivahanan, and the title of the book is Electronic Device and Circuits, and the publishers are McGraw-Hill Education. Okay, first diode equation. As you know, the diode equation, if you observe the different types of currents that are flown through the diode, already we discussed in the last class. One is by the diffusion phenomena, that is called as a diffusion current. Second one is called as a drift current. Okay, drift current and diffusion current. And if you observe the different types of currents that are flown through the diode, as an example I am drawing like this. Suppose this is a PN diode. As you know, the majority carriers in the P side are holes, and the majority carriers in the N side are electrons. So here I am drawing a curve related with the currents here. So if you observe this particular curve, this is the current due to the drift current. This can be written like this: IP. So whenever the hole is diffused from P side to N side, as you can see here at this current, I can call it as the hole diffusion current, IPN. So this is a drift current. Whenever the hole is moved to other side, that is the N side, this current is called as a hole diffusion current in the N side. Similarly, so this part. Similarly, if I observe this curve, this is the curve related with the current by the electrons, that is called as a drift current, that is represented as INN. Whenever the holes are moved from N side to P side, this current I can call it as a diffusion current. I can write like this, INP. Okay. So taking all this into account, if you go for the derivation of the diode current equation, finally will be getting this type of equation, and this is also called as a Shockley diode current equation, which is represented as ID is equal to IS into e to the power of VD upon NVT minus 1. So one by one, let us see the parameters here. So ID, I can say the diode current flowing, the current flowing through the diode. Okay, and here IS I already said about IS. IS is a reverse saturation current. So if you draw the curve of PN junction diode, VI characteristic curve, so this is represented like this. In the reverse bias, the current flown is called as IS, or a leakage current also we can call it as. So IS is the reverse saturation current. In the reverse bias, the current flown through the diode, it is called as a reverse saturation current. And VD, as you can see in this equation, VD is there. VD is the applied voltage. So if you take a PN junction diode, so what is the biasing voltage you applied? That we call it as a VD, applied voltage, by which the current will be flown through the diode. So VD is the applied voltage. And here In some books it is represented as N, and in some books it is represented by eta. So it is an ideality factor, depends upon the type of material. Ideality factor means it represents the number of recombinations that are happened inside the diode. Suppose if we take the germanium, the ideality factor will be 1, and if you take the silicon material, the ideality factor will be 2. Okay. So it is represented in some textbooks, it is represented as lowercase of n or eta. In some books it is represented as eta. Okay. And then K. What is and also here, what do you mean by Vt? Vt, as you can see here in this equation, Vt is there. Vt is called as a thermal voltage or voltage equivalent temperature. Voltage equivalent temperature, and the formula for Vt is equal to Kt by Q, where K is a Boltzmann constant. As you know, the value, a constant value is defined, that is 1.38 into 10 to the power of minus 23. These units are joules per Kelvin. Okay. And here T is the temperature in kelvins. So temperature in kelvins means if you know the temperature in centigrade, that can be converted into kelvins by making use of this formula. 273 plus temperature in Celsius. Suppose the room temperature, let it be 27 degrees centigrade. So the Kelvin temperature, capital T, is equal to 300 degree Kelvin. Okay. So T is equal to 300 at room temperature. Okay. And as you can see here, Q is there, that is the magnitude of electronic charge. As you know about the value, that is 1.6 into 10 to the power of minus 19 coulombs. Okay. Next, if you observe the value of Vt here, so Vt is equal to Kt by Q, that also can be written as capital T by 11,600. So how we will be getting that value means, as you know, K is a constant value and Q is also constant value. If you substitute these two values, you will be getting this value. And also if we calculate the Vt at room temperature, the value will be approximately, it will be equal to, Vt will be approximately equal to 26 millivolts. Okay. So this is about the diode equation. Diode equation is represented like this. ID is equal to Is into e to the power of Vd by eta Vt minus 1. So in some textbooks, instead of Is, it will be represented as I0, that is a reverse saturation current. Okay. So this is about the equation, and based on this equation, let us go through a problem here. The problem will be asking like this. The reverse saturation current of a silicon PN junction diode is 10 microamperes. Calculate the diode current for the forward bias voltage of 0.6 volts at 25 degrees centigrade. Okay. The temperature value is given in terms of Celsius. We need to convert it in Kelvin in order to calculate the value of T, capital T. Okay. So the reverse saturation current is given. Reverse saturation current. So here I0 is equal to 10 microamperes. Okay. Reverse saturation means it is represented as Is or I0. Okay. So here I am writing it as I0. Okay. I0 is equal to 10 microamperes. So temperature T is given. So temperature T is given as 25 degrees Celsius. That's why capital T is equal to 273 plus 25. We will be getting 298 Kelvin degree. Okay. So applied voltage also he had given, that is 0.6 volts. So Vf is equal to 0.6 volts. In our formula it is Vd. So Vd is equal to 0.6 volts. And here eta, because he mentioned the PN diode as a silicon PN diode, that's why N is equal to 2 or eta is equal to 2. Okay. So next we need to calculate the value of Vt. So Vt is equal to, I said a formula, T by capital T by 11,600. So here 298 by 11,600. So you will be getting this value. So T already I said 298 by 11,600, you will be getting 25.7 into 10 to the power of minus 3 volts. Okay. So finally, substituting all these values in the equation is equal to I is equal to I naught into e to the power of Vf by eta Vt minus 1. So Vf applied voltage is 0.6 volts, already 0.6 volts, and eta value is silicon, means we need to take it as 2, as you can see here 2 is there, into Vt. Vt value is 25.7 into 10 to the power of minus 3 volts. So if you go for the calculation, you will be getting the diode current as 1.174 amperes. Okay. I will be saying about the next topic, that is the temperature effects. So how the Vi curve will be affected by the temperature variations. So you need to know about what are the parameters of the diode that are varied in accordance with the temperature variations. Okay, two parameters will be varied in accordance with the temperature variation. One is called as the barrier potential. Second one is called as the reverse saturation current. So one parameter is the barrier potential. Second one is the reverse saturation current. Okay, so you know about the barrier potential. Under zero bias, due to the diffusion mechanism, the carriers will be moved from higher concentration to the lower concentration, thereby which a depletion layer will be created inside the device at the junction, by which a barrier potential will be created. Already I said about the value of barrier potential, that is V naught, represented as V naught. So V naught will be equal to 0.3 volts for germanium, and it will be equal to 0.7 volts for silicon. I already explained about that. Under zero bias, a barrier potential will be created inside the device. So this barrier potential will be decreased at 2 millivolts per 1 degree centigrade rise in the temperature. Suppose 1 degree centigrade rise in the temperature is there, the barrier potential will be decreased by an amount of 2 millivolts. Okay. So that's why here, as you can see here, this is a Vi curve under forward bias. The curves are 4 different curves are there. Okay. First one is at room temperature. I'm calling the room temperature here as 25 degrees centigrade. This solid curve is the curve for room temperature, and this curve is for the temperature of minus 75 degrees centigrade, and this curve is for the temperature of 100 degrees centigrade, and this curve is for the temperature of 200 degrees centigrade. Okay. So as you can see here, whenever the temperature is increasing, the barrier potential will be goes on decreasing. Okay. So here, whenever the temperature is varying, so first case, let us take this first curve. The temperature is very, very less. Okay. So this is the reference curve. Let us take at room temperature. This is the curve. So whenever the temperature is increased, the barrier potential will be decreased. That's why here, from 25 degrees centigrade, the temperature is increased to 100 degrees centigrade. So that's why here, the barrier potential for this one is 0.7 at room temperature. Now the temperature is increased, so that's why the barrier potential will be decreased. So that's why the curve is moved to the left of the solid curve, as you can see here. Okay. Still, if you observe this curve, the temperature is increased to 200 degrees centigrade from 25 degrees centigrade. So that's why the barrier potential will be decreased. So that's why here the curve is still, it is moved to the left of the solid curve. Okay. So this happens, why? Because the barrier potential is going on decreasing whenever the temperature is going on increasing. See here, let us take this curve. The temperature is decreasing here. Temperature is decreasing, that's why the barrier potential will be increased. So that's why this curve is to the right side of this solid curve, which is a curve at room temperature. Okay. So this is about the explanation regarding the variation of the barrier potential in accordance with temperature variation. So that's why the curve is moving towards the right side or towards the left side of the reference curve, that is the curve at room temperature. Okay. So that is about the barrier potential. Second parameter which will be varied in accordance with the temperature variation, is reverse saturation current. So reverse saturation current is, as you can see, if you go to the reverse bias, as you can see here, this is called as I0. That is a reverse saturation current. Okay. So whenever there is a 10 degree centigrade rise in the temperature, the reverse saturation current will be doubled. Okay. So first let us take the solid curve, which is the curve at room temperature. Room temperature means 25 degrees centigrade. Okay. So whenever the temperature is increased from 25 degrees centigrade to 100 degrees centigrade. So what is happening here? So this related curve. So as you can see here, the I0 value is increased. That's why here this is the curve. Whenever the temperature is increased from 25 degrees centigrade to 200 degrees centigrade, this is the status. From 25 degrees centigrade, whenever the temperature is increased to 100 degrees centigrade, as you can see here, the curve will be, the I0 will be doubled. So that's why here this is the curve. Okay, this is the reference curve, that is the curve at room temperature. The temperature is increased to 100 degrees centigrade. That's why the I0 is increased like this. The curve goes on like this. Whenever it is increased to 200 degrees centigrade, the I0 is increased and the curve will be represented like this. Okay. So this is about the temperature effect. So two parameters are affected by the temperature variation. One is the barrier potential. Barrier potential decreases whenever there is a rise in the temperature, and the reverse saturation current doubles for every 10 degrees centigrade rise in the temperature. And next, about the static or dynamic, static or DC characteristics. Okay. So if you take the curve, how to calculate the static or DC characteristics? So this is the curve or the forward characteristics of the diode. By this forward characteristic curve of the diode, how to calculate the DC or static resistance? And by the forward characteristics of the curve, how to calculate AC or dynamic resistance? That will be discussed here. Okay. So first of all, what do you mean by static? Static, as you know, whenever you are applying the DC voltage to the PN junction diode, okay, the operating point will not change with the time. Okay, it is not dependent on the time. So the resistance of the diode at the operating point can be found simply by finding the corresponding levels of VD and ID. So if you take the curve, as you can see here, if you take the curve, if you want to calculate the DC or static resistance, you can select any one point on the curve. Why? Because it is not varied in accordance with the time. So you can select any point. So in this particular graph, we selected the point here on the curve, and the corresponding value of V0 and the corresponding value of I0 will be measured, and the DC resistance calculation will be based on this formula. So you measured the value of VD and you measured the value of ID, and you will be getting the DC resistance or static resistance like this, which is represented by RD. RD is equal to VD by ID. So you need to take the curve here and you need to select one point. Okay, this is V and this is I, this is VD and this is ID. So the corresponding coordinates we need to take. This is a VD value and this is the ID value. So VD by ID gives the value of RD, which is the static or DC resistance. And then about dynamic or AC resistance. So how to define this particular resistance of the diode? Suppose whenever you are applying, instead of DC input, whenever you are applying a sinusoidal input. Sinusoidal input means the variation in accordance with the time. A sinusoidal variation we are taking here. This is the amplitude. So whenever you are giving a AC signal instead of DC signal, AC signal means I am giving a sinusoidal signal. So what happens here? The varying input will move the instantaneous operating point up and down on the characteristic curve, and thus defines a specific change in the current and voltage. So which is represented as RD, lowercase of RD, that is a AC resistance, and the formula will be delta VD by delta ID. So variation in the voltage in accordance with variation in the current. So whenever you are applying voltage, there will be variation in the VD, which in turn produces a variation in the ID. VD is voltage through the diode and ID is the current through the diode. Okay. So finite change in the quantity, whether it may be voltage or current. So how to calculate here? How to calculate ACR dynamic resistance? So the formula will be RD is equal to delta VD by delta ID, right? So here we need to take one point on the curve. Okay, here we selected the point here. Okay, the corresponding values, variation, that means we need to calculate the slope of this curve and we need to inverse the slope. So we can get the resistance here, AC resistance we can obtain. Okay, so here the slope at this point you need to calculate the slope. So simple manner is, suppose here this is a curve given and here let us take one more point. This is a P1 and this is a P2. Okay, so the corresponding coordinates let us take. So this is VD2 and this is VD1 and this is ID1 and this is ID2. Okay, so how to calculate this RD value here, the AC resistance? As you can see here, VD2 minus VD1 by ID2 minus ID1. Okay, so in this way we can calculate the ACR dynamic resistance from the given VI graph. So here, so one more way to evaluate this particular dynamic or AC resistance based on the Shockley diode current equation. So you know about this equation, the diode current equation. I is equal to I naught e to the power of V by eta Vt minus 1. That is a diode equation, already we discussed it. Okay, I naught is a reverse saturation current and V is the applied voltage and eta is the ideality factor, that will be equal to 1 for germanium and 2 for silicon, and Vt is the volt equivalent temperature, that is equal to T by 11,600, right, minus 1. So here this is the equation we got. So you know RD. So RD is equal to delta VD by delta ID. Okay, so here this can be approximately written as dV by di. Okay, so dV by di, that gives a value of AC resistance. So here I am taking a parameter G, that is equal to di by dV. Okay, so d by dV of I am differentiating I with respect to V. Okay, I know the equation like this. I know the diode equation. I is equal to I naught e to the power of V by eta Vt minus 1. Okay, so here instead of I, if I take this one and if I go for the differentiation of I with respect to V, what happens here? I into e to the power of V by eta Vt. So I naught is a constant, e to the power of V by eta Vt by, so we are differentiating with respect to V, that's why here it will be equal to 1 by eta Vt. Okay, so you will be getting this value, I naught e to the power of V by eta Vt by eta Vt. Okay, so you know this equation. So I is equal to I naught e to the power of V by eta Vt minus, if you separate this one, minus I naught you will be getting. So I naught e to the power of V by eta Vt can be written as, here I is there, I plus I naught. Okay, so the equation is like this, I is equal to I naught e to the power of V by eta Vt minus, if I separate, minus I naught. Okay, so I plus I naught is equal to I naught into e to the power of V by eta Vt. So that only I wrote here. Instead of I naught e to the power of V by eta Vt, I am writing it as I plus I naught by eta Vt. Okay, so this is G, that is equal to di by dV. So I want dV by di. So that's why final equation will be RD equation will be RD is equal to eta Vt by I plus I naught. Okay, So eta Vt by I plus I naught. So I naught, when you compare I naught with I naught is a reverse saturation current. It is very, very small. So this can be written as eta Vt by I. Okay. So I am ignoring I naught when compared with I. Okay. So that's why here the AC resistance formula goes on like this. Rd is equal to eta Vt by I. Okay. This is one more equation of AC resistance. Based on this equation, we are going to solve the problem. Okay. So this is the problem based on the AC resistance formula. So what is that AC resistance formula? Rf is equal to eta Vt by I. Okay. So the problem is determine the forward resistance of PN junction diode when the forward current is 5 milliamperes at T is equal to 300 degree Kelvin. That means at room temperature. Assume silicon diode. Silicon diode means eta value will be equal to 2. Okay, T is equal to 300 degree Kelvin means that is at room temperature. Okay. So what is the formula we got here? Rf is equal to eta Vt by I. So eta value given, why? Because silicon diode, eta is equal to 2, and Vt value, Vt means volt equivalent temperature, and the formula is this one. And if you calculate the Vt at room temperature, it will be approximately equal to 26 millivolts. Okay. Okay. If you go for calculation. So I value, what is the I value given here? I value is 5 milliamperes. So if you substitute all the values here, Rf is equal to eta Vt by I. Eta means 2. So Vt formula I wrote here, T by 11,600 by current I is 5 milliamperes. So that's why 5 into 10 to the power of minus 3. So 2 into, so T value room temperature means 300 degree Kelvin by 11,600 into 5 into 10 to the power of minus 3. You will be getting 10.34 ohms. Why? Because it is resistance, forward resistance. Why? Because forward bias, we are calculating the forward bias AC resistance. So that's why here Rf is equal to, we are getting 10.34. Why the resistance value is very, very small? In the forward bias, what happens? In the forward bias, maximum current will be flown. Okay. So that's why the resistance will be very, very small. Current is maximum means the resistance will be small. So that's why, as you can see here, we are getting a smaller value of resistance. Why? Because the diode is forward bias. As you can see, forward resistance means the meaning is the diode is forward bias. In the forward bias, the resistance will be very, very small. In the reverse bias, the resistance will be larger. So finally, I am recapping the things, whatever happened. So first, I explained about the diode equation. Based on that, we solved a problem, and then we discussed about the temperature effects on VI characteristics, and then we discussed about the static or the DC resistance, and then we discussed about dynamic or AC resistance. Okay, with this, I conclude my video lecture presentation. Thank you.